This is part 2 of the video lessons for the topic 8.7 in the AP Calculus curriculum, cross sections, volumes of cross sections, squares and rectangles. We just did calc part 1 where we calculated the area of region of a curve. We reviewed that. Now we're going to describe to you what we mean by a cross section that is a square or a rectangle. What we mean by this is if we are given a function like we did in the first part, let's say that we have f of x equals x. And we know the graph of that. And let's say this time let's go from 0 to 3. When we're dealing with volumes with cross sections, what we're suggesting is that there's a region under the curve or between curves that forms the base of a solid. And so what we're going to do is we're going to calculate the volume of that solid. When we say that we're going to calculate the volume of solids, what we're saying here is that if we're going to do this from 0 to 3, that region from 0 to 3 forms the base of a solid. And if we're going to use square cross sections, it means if this side is represented by this line, and this side represented by this line, and this is the base of the solid, then if there's square cross sections, this is going to form a three-dimensional object where that looks something like this, almost like a pyramid. It's a pyramid, but it's laid over on one side, where this is the part here, and there's at each one of these places, there is another cross section that protrudes up like this until all together they pull down and form this solid. And our goal is to calculate the volume. And we do that by looking at this. Let's see, get an eraser. I'm going to pick one cross section out of there. One single cross section. So remember when we calculated the area under the curve, we were summing an infinite number of rectangles where the width was dx and the height of that rectangle was whatever the y value of the curve was. In this case, it's y equals x. And so what we're saying is, if this volume is formed by square cross sections where that region is the base of the solid, then that rectangle that we would have summed to find the area also, oops, it's wrong. Trying to get my eraser. Protruding out from that rectangle is a square. It's really a rectangular prism where the base of that rectangular prism, this is dx and this is x, and this is the actual cross section. Because it's a square on its face, the height is also x. And so the volume of this one individual cross section is going to be x times dx. So for a square cross section, what we have to know is the height, if we could view that as protruding out from the, if we view this as a three-dimensional thing, it protrudes out the same as it goes up to from the x-axis to the curve. So the height is as long as the width is the dx, the length is the x, and the height protruding out would be x also, because they're square cross sections. And so if we're going to find one volume, the volume of this one cross section, oops, let's go back to draw, is going to be x, it's whatever f of x is, we'll do another one here in a minute, times x, length times width, times height, times dx. And so the volume of one cross section is x squared dx. But remember, if we want to do an infinite number of these, if we want to find the volume of this entire solid, that's the volume of one particular cross section. So we're going to sum, we're going to do all of these from 0 to 3. So we're going to put those as our limits of integration, and we're going to sum all of the equations, or the expressions for the volume of each of these cross sections. When I sum this, it's going to give me the volume of that pyramid that we showed you a few moments ago. And so this is going to be, if we evaluate this, it will be 1/3 of antiderivative is 1/3 x cubed, evaluated from 3 to 0. Whoops. Or sorry, 0 to 3, which is going to be 1/3 times 3 cubed minus 1/3 times 0 cubed, which is 27 over 3, or 9 units cubed, whatever those are. That's what we mean by volume with cross sections. And that's part 2 of the video, of the lesson.